Tonight, I just wanna take you high. Throw your hands up in the sky. Let's see those layers up high. What is atmosphere that brings up to the moon? First, troposphere, that's true. Stratosphere has it, ozone in the air. Mesosphere, cold layer, and thermal. Let's stop, it's all live, all live, all live, all live. Troposphere begins. Oh, they don't know, oh, they don't know. The next is stratosphere, the ozone's in. Where the showers blink, near the Euro trend. Mesosphere breaks them loose. The next is dark ionotic zone. Thermosphere is spreading out the fuse. This, it is close to the land. Troposphere is at the bottom. First up. So next is stratosphere around it, and the ozone in the spot. Next up. Mesosphere, cold and flames. Thermosphere, y'all the hottest. Next up. Layers on it. Come on. Atmosphere that brings up to the moon. First, troposphere, that's true. Stratosphere has it, ozone in the air. Mesosphere, cold layer, and thermal. Weather's here, water cycle. Thunder. 12 cams, troposphere, it will end. Will it reach? Will it reach? Stratosphere, 50 cams, it is here. Third, mesozip, rocks are lit. Send and plunge in those steroid spin. Thermos lab. Ionosphere, we see it. Exos next. It is dissipating. It is close to the land. Troposphere is at the bottom. First up. So next is stratosphere around it, and the ozone in the spot. Next up. Mesosphere, cold and flames. Thermosphere, y'all the hottest. Next up. Layers only. Come on. Atmosphere that brings up to the moon. First, troposphere, that's true. Stratosphere has it, ozone in the air. Mesosphere, cold layer, and thermal. Troposphere we go, they be like, oh, low layer. Stratosphere we go, they be like, oh, so layer. Mesosphere we go, they be like, oh, cold layer. Now, thermosphere is last like, Atmosphere has it, atmosphere has it, what's that sound? Atmosphere has it, atmosphere has it. Come on now. Atmosphere has it, atmosphere has it. Don't spike the ceiling, keep us from freezing just. Atmosphere that brings up to the moon. First, troposphere, that's true. Stratosphere has it, ozone in the air. Mesosphere, cold layer, atmosphere that brings up to the moon. First, troposphere, that's true. Stratosphere has it, ozone in the air. Mesosphere, cold layer, and thermal.
So welcome to this lovely Wednesday. I'm so excited to be here with you today. We are going to talk about the project a little bit, and I'm going to check in with y'all and see what we can do, and then talk about some of the assignments for the week, and then I have a little lecture that I want to continue from last week about the atmosphere, and we'll talk more about the factors that influence temperature more specifically. I know I mentioned them last week, but this week I want to make sure I go through them in a little more detail. So, all right, so this week there's a couple more chapters. There's one on circulation, and I'm going to show you a map and talk a little bit about that here in a second. And then you're also going to read about atmospheric moisture. So, all right, so this week, one of your activities is to create a map of the ocean currents and the winds. So, and there's some color things. It's like, make this red, make this blue, you know, make this green, you know, label this, label that. If you're not in the mood to do coloring, which is fine, although, you know, it's better for your brain if you do, meaning for, you know, recall and stuff like that, but you don't have to. You could do it all using pictures. You could start with these two pictures. This upper picture is a picture of the wind patterns in on the world, and then this is a picture of the ocean currents. And these are a good start, but they're not enough. And they're not enough because I've asked for each of the currents to be labeled. So for example, the California current, which is the one that goes by California. Yeah, it's hard to figure out some of these currents. But this blue one that goes by California is called the California current. And, you know, these are only the major ones. This is showing you like the Gulf Stream and things like that. But there are others. These are all named. If you look at the activity, it tells you what to do. And again, so it's like, you know, use brown, not green, all the land masses, including Antarctica. So what you would do is find a map that shows the land masses that are, each one is colored, you know, they can all be the same, but they should be labeled. It should say like Asia and Europe and Antarctica and stuff like that. So it needs to be labeled, all right? And then all the water, obviously, and then those should also be labeled. Of course, if you look back at this, that it's labeled here, Pacific Ocean, Indian Ocean. So a lot of them, so like this one here would work for the first two, they're brown and blue. They don't have to necessarily be brown and blue. You just need to know, you know, kind of what they are. And then it wants you to draw these lines. So that one's a little more complicated to get a map that only has 0, 30, 60, and 90 in the northern and southern hemispheres. Because this one is done in 20s. They do exist, but those numbers are important, and you'll see why. Oh, look, it's over here on this map. That's right, done with that one. And again, I share these, so all you have to do. But here are all the ones that need to be labeled. We used to have, back when I first created this, you can just Google ocean currents labeled. You may have to come up with two different ones, like one for the warm currents, one for the cool currents. A lot of times they're not all, so make sure they're all labeled somewhere in those pictures. So you may need like 3 pictures in order to get these, you know, labeled, all of these labeled, but make sure they're all in there. So don't just cheeseball it and give me, you know, the one I gave you, because that one, that's not going to work. Only a few of them are labeled. And then this is just how to do it. And then this is the trade winds, which is in that picture up here. So this one would be fine for the trade winds. So this one's good for the winds. This one's good for the oceans and the continents, and the reds and the blues. But you want to get them so that they're labeled, so you know, like, well, I don't know. Yeah, you need to make sure that they're properly colored, in my opinion, because the idea is that you'll have the resource available to you, so that you would know just by looking at this resource that the California current is blue. So if you were to put this and then just have the ones labeled, that would be fine, but put them like right next to each other or right on top of each other on the same page, so that it gives me the impression that you understand that, you know, here are the currents in color and here they are labeled, so that you can quickly figure out which are which. Because if you get asked, you know, what is the name of the current that travels, you know, past the east coast of the United States, and you should know where the United States is, or North America is. So if you don't know your continents, make sure you find a map that has them labeled, or label them, because you may come across questions that ask you questions about, where certain currents are. So like, what's the name of the major current that circles the Tropic of Capricorn in the Atlantic Ocean, which is why these things are asking you to label certain things. So it's like, label all the oceans and stuff like that. All right. So, and then here's the map if you want to color it yourself. That also works. So hopefully I'm as clear as mud on that particular one. All right, so last week we talked about the factors that influence air temperature, and I told you the mnemonic device I created for you is Lower-in CV. Again, that stands for latitude, ocean currents, winds, elevation, relief, nearness to water, clouds, and vegetation. And I'm going to take some time to talk about how these are influenced, how these factors influence air temperature one at a time. So we'll start with latitude. So latitude deals with two different things mainly. That is the angle of the sun's rays. And if you are familiar, we talked about incoming solar radiation, and we've talked about the imbalance and how the amount of energy is concentrated around the equator and how it spreads out at the poles. And so that has to do with the angle of the sun's rays. So the more direct they are, the more likely you are, the more energy that you're receiving. And so it's typically warmer, whereas the poles are, colder, terribly cold. They're never warm. And that's for two reasons. The angle is very shallow, so the energy is spread out. And the other thing is that they even if the day is 24 hours long on the North Pole, for example, for 6 months out of the year, they're getting 12 hours of darkness. It's going to be bitterly cold. But even when it's 24 hours of light, the sun is too low on the horizon. It doesn't get particularly warm. So, and that's how, so the easiest way to describe that is the higher your latitude, the lower your temperature on average. The next factor is ocean currents. Why isn't it going? Oh, there it is. Okay, so ocean currents also affect the temperature of a place. So these currents can be warm or cold. And when the air blows over the top of them, the air gets their warmth or cold based on what type of current they're traveling over. So what we call the North Atlantic Drift, which is the area as it leaves North America, travels across the ocean towards Western Europe, is what keeps that particular area warm. In fact, many have said if the ice sheet on Greenland were to melt, it would cause that North Atlantic Drift, which is just a carryover from the Gulf Stream, to slow down and could thrust Europe back into another ice age. So yeah, they need that warm current. And one of the main reasons why we in California don't get hurricanes is we have a cold current off our coast, and hurricanes need warm water in order to gain power. So even if it starts as a hurricane out in the Pacific, which we don't call them hurricanes, we call them cyclones and typhoons simply because of the ocean that they're in. But as it travels closer to the west coast of the United States, it's going to lose its steam, so to speak, because of that cold current. So And so, yeah, I talked about oceans currents. Okay, cool. The next one is winds. So winds indirectly change temperature of a place according to which way they blow. So for example, in Southern California, if we have an onshore wind, that wind is going to be cooler than an offshore wind that's blowing from the land out to the sea. For example, the Santa Anas are a good example. I love that we call them Santa Anas, even though they were really called the Santana winds, like the devil winds, because they come from the land and they're typically more dry because they've lost their moisture. But so we have prevailing winds, which is onshore or offshore. There's the westerlies and the easterlies, which you're going to put on your map and stuff like that. But there's also local winds. So during the day, as the land gets hotter than the sea, the heated air over the land becomes lighter, it rises, and then as it rises, the pressure decreases over the land, and so winds like pits, winds like people, in my opinion, but definitely like myself, right? If I walk into a crowded place, I am trying my best to find a spot that's not as crowded. I like my space. I'm a big fan of this, 6 feet of social distancing, because that means that nobody's getting close to me, because I don't like people near me. It's really kind of weird. I've never really liked, which is why I like being in 29 palms. There aren't as many people to be around me. But so wind or air goes from areas where there's high pressure to areas of low pressure. And that's why the wind blows. If there's like a significant difference, then it's going to blow faster or harder, depending on how you want to define, wind as being, if it's going faster, it's blowing harder, but it's the same thing. So that would be like a local wind. All right, elevation. So yes, the temperature does not depend on latitude alone, for interesting reasons. So like, for example, Mount Kenya, which is in East Africa, is on the equator, but the top of it is always covered in snow because it's like 16,000 feet in the air. And the Bermuda Islands, where the Bermuda Triangle is at 30 degrees. And they never see snowfall there, even though they're essentially, they can be at the same latitude as a place that does receive snowfall, for example. I have a couple of maps. So if we look at these 2 cities in India, which are really good examples. So you have this city here, which is next to the ocean, and this city here, but we're talking about elevation. So the green means it's higher in elevation. So if I look at the satellite view, it's gonna be some giant populated mass, but this area here is actually higher in elevation. So let's go back to my map, because and because of that, or here's a better example. These 2 towns here, these are at the base of the Himalayas, and this town is down in the valley. So this one's going to have a lower temperature, even though they're at the same latitude. And that has to do with elevation. And there's 2 parts to that. There's what we call the adiabatic rate, which is the rate at which air cools based on elevation. So if you've lived in Southern California for a long period of time, if you've ever, like if it were clear right now and you could see the mountains, they probably are covered in snow, and yet there's no snow in your front yard, right? And you're at about the same latitude, essentially. I mean, they're a little bit, because they're behind you, I guess they're like, 0.1 degree of latitude different, but for the most part, you're at the same latitude, but they're covered in snow and you're not. And that has to do with elevation. As you increase in elevation, you're going to decrease in temperature. And there's a specific rate that happens at. The easiest way to think about it is for every 1,000 feet, you're going to lose 5 degrees of temperature. So not a bad gig. So, you know, like Glendora is probably at, you know, maybe 1,000 feet, maybe 1,500. And the top of Mount Baldy above Claremont is at 10,000 feet. So if we're at 2,000 feet and they're at 10,000 feet, that's an 8,000 foot difference. That's 40 degrees. So if it's 40 degrees at your house, it's 0 degrees there, right? So you can see why it would snow there and not where you're at. So. And then last week I showed you the Steve Spangler video on temperature inversion. And that again is when the warm air is on the top or on the bottom. Does anybody remember? Where does warm air belong?
She said top. Is that right?
Oh, okay, good, good. A temperature inversion occurs when the warm air is on the top. Very good. Remember, warm air is supposed to rise, so that's naturally where it's at. But what we want in a normal system is that the warm is on the ground, and so you get that convection occurring, right? So temperature inversion, normally the cold air, like I said, if we increase in elevation, we're decreasing in temperature. So as you go up, the air should be cooling off. If you go up in elevation and it gets warmer, you're in the middle of what we call a temperature inversion. So, but that's not normal. It's not supposed to happen normally. But there are reasons why it happens, but yeah, the normal way is you increase in elevation, you decrease in temperature. So those are just pictures of the same thing, talking about dew points and stuff like that, which you'll learn a little bit about in a minute here. I have another slide about that. All right, the next one is relief, and that has to do with which side of the mountain you're on. So, for example, at let's say 2,000 feet on the south side of the transverse range, which is where Glendora is at. If we went to 2,000 feet on the other side of the mountains, you're in Palmdale. And if you've ever been to Palmdale, you know there's a significant difference between Palmdale and Glendora in what the vegetation looks like, or the temperature for that matter. In fact, it's warmer, even though they're at the same elevation, it is actually warmer in Palmdale than it is in Glendora, because of the fact that they're on the opposite side of the mountains, and because they're on what we call the rain shadow side or the leeward side of the mountains, they're in a, as the air descends down the other side, it's going to warm, but it's going to warm faster than it cooled because of things related to humidity, which again, I'm going to talk about here coming up, but I wanted to go through these. Nearness to water, that has to do with, you know, being next to the water. Obviously, it's going to moderate your temperature quite a bit. So it's really hard. It takes a lot of energy to heat water versus air. So if the wind or if the area is near water, you're going to have either a warming or a cooling effect, and it's going to keep it what we call moderate. So for example, daytime temperatures versus nighttime temperatures, if you're near water, is a smaller number than if you're not near water. So for example, out in the desert, you can see a temperature variation between daytime and nighttime temperatures between 20 and 50 degrees. But next to the ocean, you're probably, you know, 10 to 30 degrees or so. And that has to do with the idea that there's a lot of energy that is stored in the water, and then it's not released at the same rate as it is on land. And then there's that.
Did it recording?
I'm sorry, what? Oh, okay, cool. Not me. Cool. All right. And then there's clouds. Clouds in the sky can also affect your temperature. The presence of clouds in the sky prevents the amount of solar radiation coming into the Earth's surface. It also prevents ground radiation from going back out. And because of this, places where there are less clouds experience a high day temperature and a much lower night temperature, such as the condition here in the desert. In the equatorial areas, because of the abundance of cloud cover, day temperatures are not as high and night temperatures are not as low. So I should actually, let me go back a second to talk about nearness to water, because I kind of flummoxed it a little bit. I mean, yes, it is, but I should have saved the conversation about the ocean versus the desert for the cloud conversation, because that's more of an impact. Nearness to water is like the difference between Santa Monica and the Inland Empire, or even Los Angeles. So like downtown. So if you're in Santa Monica, you know, it's going to be cooler than, you know, 10 miles inland or 20 miles inland or 30 miles inland. That has to do with the nearness to water. I should have, so rewind. So when we talk about nearness to water, we want to talk about areas that, you know, are close to a big body of water. So for example, Chicago. So it's not just the ocean, it's any large water mass of water. So Chicago, you know, is going to be more impacted. So it's going to be cooler in Chicago than it is going to be down in like Springfield, right? So, or something a little more closer to home, you know, Huntington Beach or Santa Monica versus downtown Los Angeles. And for those of you who, you know, go to school in Glendora, but maybe live in, say, you know, Rancho or Fontana or somewhere like that, you know that the temperature between those two places is significantly different. So yeah, all right. And then clouds, that again, we'll go back to the comparison I made between the beach and the desert. That's why they have those huge swings in daytime and nighttime temperatures. So I apologize. Please forgive me. All right. Moving on to the next thing, vegetation. So one of the things you may have read about is something called albedo. And albedo is how reflective a material is. So, for example, oh, albedo, sorry. I'm like, what was I talking about? Albedo is how reflective a material is. So for example, snow has a very high albedo. It, you know, reflects a lot of the energy that comes in. And water or land or, you know, stuff like that. A better way of looking at this, in my opinion, is really to talk about urban heat islands, or if I was to tell you you had to stand outside in August, you know, where would you rather stand? You know, on top of the roof of a building, which is, you know, lightly colored, or the asphalt? You'd be like, okay, I'll take the roof top of the building because it's going to reflect a lot of that heat energy and not store it up. For those of you who have ever, you know, driven in the summer or looked out across the ground in the summer, it kind of looks like there's stuff evaporating off of it. That's actually heat energy that's heating up and creating like atmospheric water vapor that you can kind of see rising out of the ground. So that has to do with albedo, how reflective the surface is. And one of the things that we talk about is what we call urban heat islands. It's the idea that if you go to, say, downtown Los Angeles, because there isn't a lot of green space and stuff to kind of reflect, or in this particular case, absorb incoming solar radiation, because vegetation is going to absorb said energy versus all these reflective concrete and asphalts and things like that. So cities or urban areas are typically warmer than rural areas. And so that's it, lowering CV. All right, so there are also factors that affect air pressure. And if you recall the video with the guy walking around before the guy jumps out of a plane and starts, surfing on the wind, he talked about we're like lobsters at the bottom of the ocean. We got all this pressure around us. But the factors that affect air pressure, this is I literally at one point was like, hey, I need a picture of the Earth wearing a hat. And this is what I came up with, because the mnemonic device I have for the factors that affect air pressure are hat. So they are humidity. Oh, these are all inverse relationships. So as one goes up, the air pressure goes down. And as it goes down, the air pressure goes up. So they're inverse relationships. Okay, so let me go forward. Humidity, as the humidity increases, pressure is going to decrease. And as the humidity decreases, the pressure is going to increase. So again, they're opposites, right? Or inverse is what we call them in mathematics. Same thing with altitude. So A stands for altitude. As the altitude increases, the air pressure decreases. If you've ever taken like a bag of chips up to the mountains, you know this because the bag gets all puffy. Or one of the things I used to do on a daily is I had my little water bottle and I would, cap it at the bottom of the hill. And by the time I got to the top of the hill, when I opened it, it popped. It would be like poof, and like water sometimes would like. So I had to remember to drink enough water so that I didn't spray myself in the face when I got to Victorville. After teaching in Citrus, I always taught in Victorville, which is kind of interesting because that's what I'm still doing, even though I'm sitting in the same spot. I still go from here to there, which is kind of cool. It just worked out that way. So again, or one of the cooler things is to take, like a plastic water bottle, not a hard one, but like a regular, not that I'm condoning this behavior because there's too much plastic in the world, but if you are one of those people who still uses those plastic bottles of water, go up to the mountains, cap it and come down, and it'll be like all collapsed in, which is cool in a sense. But I was driving, I had come up to 29 Palms and I had one of those new plastic bottles of water, and I drank a little bit and drove down to my house. But by the time I got there, the bottle, because it's like recycled plastic or something, or I don't know, there must have been some manufacturer's defect, but there was water all inside my cup dispenser in my car. Like it had like filled up, because when the bottle collapsed, it cracked and the water just oozed out. So I got home and I was like, I don't remember drinking this much water. And I looked in my car and I was like, oh my gosh, it's like all inside my cup holder. It was like a little ocean of water. So anyways, temperature, again, inverse relationship. So T stands for temperature. Remember, the mnemonic device I have is hat, humidity, altitude, temperature. Again, as the temperature of the air increases, the pressure is going to decrease, and vice versa. So if the temperature decreases, the pressure is going to increase. It's just like people. I've always described air pressure like people. So when you get hot, you don't want people to be around you. You like throw clothes off because you're like, I don't want anything next to me. But when you're cold, you like put tons of stuff on and you're like, hey, let's share some body heat, right? Same idea. Right, you get cold, so the air molecules also want to do the same thing. So they, so yeah. All right. The factors that influence wind. I don't have a cute mnemonic device, but I do have this cute little seesaw picture. I don't know how many of you remember being on a seesaw as a kid, but I loved being on the seesaw as a kid when I was growing up. They used to have these huge bike racks at the elementary school, and we would stack them on each other kind of like this, and then ride the bike rack up and down. So one person would stand on this side of the bike rack and the other one would stand on that side of the bike rack, and there was a bike rack that went across this way. Yeah, so we used to stack them up like that, use them as a seesaw, because you'd get really high, because they were like, 50 feet long. They were like ginormously long. So anyways, so as I said before, wind is like, get me the heck out of here. There's too much pressure. I want out. Get me out of this pressured situation. So you're going to run from areas of high pressure to areas of low pressure. So that's kind of what this is showing. And you can see the low pressure. That's Miss Pitts. This is what my mom wanted me to look like. She always permed my hair. My mom had red hair, and she always wanted a red-haired kid. The closest she got was blonde. All the rest of my siblings have brown hair. I have blonde. I kind of wish I had red hair. That would have been kind of cool. Thought about dyeing it, but I think I would look weird. I wouldn't get used to it fast enough, and then I'd be like, oh my gosh. All right, so a couple of things that influence wind is what we call pressure gradient force, and that has to do with how different they are. So the larger the difference between the two air masses or weather systems, depending on the case, the faster the wind is going to go there. So that's what we call pressure gradient force. And the other thing that impacts wind is what we call the Coriolis effect. And so it's caused by the rotation of the Earth on its axis. And I think my next slide is the video. I hope it is. And then I'll come back and I'll talk a little bit about this. Yes, cool. All right. I didn't show you this video, did I? I hope not.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
All right, here's the game, right? You're going to throw the ball straight. So what's your name? Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
yeah,
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude?
I was going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
Whoa!
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah,
Sucked.
I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to, and that, ladies and gentlemen, is the Coriolis effect.
All right, so, oops, how do I go? No, I don't want to watch the video again. Okay, so, these pressure gradients and systems are constantly moving, constantly changing, but due to the Coriolis effect, they have what we call a deflection or a curving of the object. It's caused again by the rotation of the Earth on its axis. That's why he did it counterclockwise, because in the northern hemisphere, if you looked at the top of the Earth, it looked like it's going counterclockwise. So objects curve westward or to their right in the northern hemisphere. The effect is greatest at the poles and not as great down by the equator. Again, it's an apparent deflection because of kind of sort of where we expect it to be, but because the Earth is rotating. So this doesn't just happen to wind, this happens to ocean currents also. And the faster the object is moving, for example, like a plane or a rocket, the greater that effect is going to appear to us. So for example, in the northern hemisphere, it's going to turn a high pressure system clockwise. So that's what we call an anticyclone. But if it's a low pressure system, then it's going to turn it counterclockwise. And you're like, wait, what? That doesn't make any sense. Okay, remember, we get cyclones. Cyclones is just another name for a hurricane, right? It's just the cyclone occurs, well, all hurricanes are cyclones, but not all cyclones are hurricanes or something like that. But we can also have, so that's going to go counterclockwise, because if you look at it in the northern hemisphere, where we're at, it's going to deflect. We're at like 33, so it's going to deflect to the right. So that's going to be clockwise, right? But anticyclone is going to be, which is kind of weird, is also clockwise versus a cyclone, which is counterclockwise. So it's one of those confusing things that we in geography like to do. But that's because he who makes the maps, or in this case, he who defines the terms. And so the first place that these cyclones were found was in the southern hemisphere. Or, sorry, not where they were first found, but where they were first like, hey, this is kind of weird. So yeah, they call them cyclones. And then if they go the other way, they were called anticyclones. So it's kind of crazy. But anyways, more about that at a later date. Okay, so we now understand the Coriolis effect. We already watched that. Okay, and then another thing that's going to impact wind is going to be friction. So I don't remember, did I show you the upwelling video with the guy with the vacuum cleaner blowing it across the top of the water? I'm trying to remember if I showed that to you or not. Yes, I did. No, I didn't. Anyone? Here, I'll look in the chat to see if anyone's. Anyone? All right, well, I guess the easiest way to think about it is if you have something moving over the surface, whether it be water or wind, where it has friction, it's going to slow down, right? So everything that's in contact with the surface is going to be slower than the air above it. So if you go, for example, up into a building, like higher into the building, the wind is actually moving faster than it is down on the ground. So I installed a weather station at my house, and one of the things it says is, you're supposed to put it at least, 3 feet off the top of a building and at least 10 feet away from any, 10 feet away from any building that's taller than the top of your weather station, so that you're not catching that wind. So it's kind of a crazy idea, but anyways, so again, it's going to change the not only the direction of the wind, but also how fast the wind is moving. So another thing that is a friction type situation as it relates to wind is if you've ever been out to the Coachella Valley, and as you're driving from the Inland Empire and you are essentially leaving Cabazon and just before the, so from that area from Cabazon to the other side of the 62, essentially when you're getting into the true Coachella Valley, it's always windy there. Where all those windmills are, it's always windy there. And that's because of all of that air that's from the ocean and from the basins to the west are funneled through one spot. Similar to the idea that, if you live in, say, Fontana or Rancho Cucamonga, it gets windy there a lot. And that's because the air mass that's above the Cajon Pass is coming down that way. And the air that's below the Cajon Pass or south of the Cajon Pass has to go up through there. So you're getting wind in that vicinity almost all the time because the air is being frictionally forced and directed through one spot. So, all right. I don't want to talk about that. So I do want to talk about this. Again, this is going to be part of your activity this week, your coloring activity or your map finding activity. So we have, and they follow each other, meaning north and south of the equator, you have the trade winds. So these are called the northeast trade winds. These are called the southeast trade winds. And you look at these and you're like, how is that possible? Winds are described based on where they come from, not where they're going to. So these are coming from the northeast. These are coming from the southeast. So it's another one of those weird things about winds. But in between, you have what we call a doldrum. So if you remember studying history and talking about the merchants and people like that traveling across the planet, they relied on these winds when they had their big sailing ships, Columbus and his Nina and his Pinta and his Santa Maria and all of his issues, used these trade winds in order to get places, right? So or if you ever, watched movies and they're traveling across the ocean, the trip from Europe to the United States was much faster than the trip from the United States back to Europe, which is why a lot of times they would travel up this way and then back down, because they were able to catch the polar easterlies. That's what these are called here. Which naturally go this way, so they could catch these guys and get like a tailwind kind of thing. So we have trade winds and westerlies, and then and then in between we have what we call the horse latitudes. It's kind of like the in between areas between these two different types of winds. It's kind of like there isn't a lot of wind. So. You'll learn about the different, you'll learn about, you know, daily or period, what we call secondary or periodic winds, you know. The cool air at night sinks into the valleys and the warm air rises during the daytime, unless there's a inversion layer. Then we have local winds called land breezes and sea breezes. Go. Why isn't it going? Oh, is that the last slide? Oh, that's the last slide. Sweet. All right. So let me look at the discussion for this week. I can't remember what it is. I know there is one. Oops, wrong school. Right idea, wrong school. All right, let's see here. Quiz, atmosphere 2.0. Oh, that's right. You're gonna watch a video. It might be the video I already showed. Can't remember. Oh no, it's on ocean currents and climate. Okay, I remember now. That's a cool one. I like this video. So maybe we'll watch that right now. So you're going to watch these 3 videos, and you're going to basically describe using the resources or something you remember, you know, according to the National Geographic video, the relationship between atmospheric and oceanic circulation is blah, blah, blah. So you want to kind of quote some of these things and make it seem like you watched all 3. So maybe have like a factoid or a quote or a source from each of them in your response for this week. And then, you know, you can use other sources too. Especially I've seen in the past, students have referenced other sources typically in their response posts to others rather than their original posts. So most of the time, and I'm not saying you have to do it this way, just, you know, putting it out there. The first video you would watch, the first, your original post, you talk about each of the 3 videos and in your response, and then you can use those same 3 videos in your reply to people, but you should have, you know, like something from the videos in your responses and your replies, if that makes muddy sense or not. I'm sorry. So, all right. Are there any questions? This is the same video. Let's see. I thought there were only 3 videos. Ah, that's it. That one doesn't work. Oops, that's bad. Okay, I'm gonna have to fix that one.
We have a question.
Okay.
Can you post the PowerPoints? Last week we couldn't find it at all anywhere.
Okay.
Wrong
Let me
place.
double check and make sure I put it in the spot I think I put it in, and then. Yeah, okay. So if you go to the home page where it says Zoom recordings and Google Slides,
Okay.
this is the recording here. And these are the slides that I presented last week. So I'll do the same thing when I get the recording back. I'll put the Zoom recording and the slides that I used today in the same spot.
Okay, great. Thank you.
You're welcome. And I have to fix that last link because I don't know what I did wrong, but I gotta fix that. So I will fix that right quick. Big link numero 3. I knew there was something I needed to do. Okay, and then there's a quiz, and okay, I need to do that. 20 points. Does not belong there. 10 minutes. Must be 10 questions. Multiple guess. Highest 3 after the last attempt. That is not when you're going to see your responses. You will see them next week. So I will fix that too. All right. Now, a couple of other things. Let me double check. If I go to assignments. So your group project is due on the 27th. I don't know if these were in before, but I have put in the rule that the lowest score for your discussion and the lowest score for your quizzes will be dropped. So that should help some of you who are struggling with getting those turned in. Actually, this should actually be 2 quizzes. So I will fix that, hopefully. But does anybody have any questions that I can answer for the good of the group? I'm going to stick around if you need. It's not necessarily for the good of the group. It's just for the good of you. So, but I want to make sure I answer any questions before I stop the recording for this week. But I thank you all for coming. I appreciate your time and effort. Enjoy your readings this week. We're getting dangerously close to our first test, I think. So more about that, I think in 2 weeks, because we still have to talk about the hydrosphere some more. So yeah. All right, well, have a good week, everyone. Again, I have office hours tomorrow if you need me, or shoot me an email. I have a tendency to be around to be helpful. And excuse my yawning, goodness. Air, it's the pressure change in my brain. So, all right.
One more question.
Sure.
On this map thing, I'm wondering if it's going to be labor intensive for her to type out all these labels. Are you okay with me just handwriting stuff in?
You don't even
her?
need to do that. You can just find the pictures on the internet with it already labeled.
Okay,
You
great.
can just put together a whole bunch of maps. Everyone can do that.
Oh, great.
So it doesn't have to be hand done at all. You can just find a whole bunch of maps that have the information. Just make sure that you have all the information, and you want to try and get it into as few maps as possible, because you don't want to have to, if you need to reference it, have 6 pages of maps to look at. But to each his own.
Okay, great. So much. Okay, great.
You're welcome.
Okay, bye. Thank
Bye.
you.
Bye. Stop sharing. Okay. Stop the recording.